the Division of Planetary Science of the American Astronomical Society in the past. Bitsch B, as he is known in his long list of publications, also has been invited to many seminars and conferences. In addition, he has exercised his supervision to many undergraduates, postgraduates, and PhD students, and currently is teaching at the Heidelberg. I welcome Dr. Bertram Bitsch to take over.
Yeah, thank you very much for the introduction. It's a great pleasure for the invitation, and I'm happy to give this talk. So I'm looking forward to the discussion. Let me share the screen of my presentation. Yes. So thank you very much. So I will talk to you about the formation of superEarths and the Mini-Neptunes. And before going into the details, I would birthplaces of planets, and these are so-called protoplanetary disks that consist mostly of gas and to a small percentage of dust. What you actually see here in this image is an image taken with the ALMA telescope in Chile. It's already a few years old, but this picture greatly influenced our perception on planet formation, because planet formation happens in these protoplanetary disks, but we never really imagined all these beautiful substructures that we can see in the disk. So this image here is from HL Tau, a nearby planetary disk around it. You see from the size bar that the disk is actually probably like 100 to 200 AUs, astronomical units in size. And we see a lot of different substructures in this disk. We have bright rings and gaps that are not as bright, where maybe they are devoid of material. And these disks we can now observe in a great level of detail, which we can now influences our way of thinking of a planet from in these protoplanetary disks. And we can actually observe planetary systems directly. You see here a system of 4 different planets that are orbiting on very wide orbital distances. You see here the bar, so this 20 AU bar. So these planets orbit really far away from the planet. In comparison, if you plot here in white the orbit of Neptune in our own solar system, which orbits at around 30 astronomical units from our central star. So this is a very wide planetary system with several times the mass of Jupiter. So this is a very extreme planetary system that we can also observe. In reality, of course, we can observe also different types of planets. So the outline for my talk is how can we explain the diversity of planets. For this, I would first go a little bit into exoplanet observation, so how can we observe planets around other stars, and then go a bit into statistics of these exoplanets, so what different types of planets do exist, how common they are. And then I will talk about the planets can actually form. Then we'll focus then specifically on a formation scenario for the formation of superEarths, and then I will talk about the composition of these superEarths and mini-Neptune-like planets. So how can we detect planets? There's 2 main detection methods for detecting planets. One is the radial velocity method that you see illustrated here in this cartoon, where the idea here is that we observe a star, and an unseen planet that would orbit around this star would actually pull on the star, change in the light of the star that we observe. So depending on how the planet actually orbits the star, we would see a blue or a redshift from the light, depending on how the planet is in its orbit. So if we then observe a full orbital period of the planet, we see the full change in the light curve. Actually, the first exoplanet around the main Cephus star was detected with this radial velocity method by Mayor and Carlos in 1995, and they actually received the Nobel Prize for this. How we can detect planets is the transit methods. The idea is actually very simple. We observe a star, where we can observe the brightness of the star, and as soon as the planet moves in front of the star, we will see a dip in the brightness, as illustrated in this cartoon. So once the planet crosses the face of the star that we observe a dip in the brightness. With this technique, we can actually determine the radius of the planet relative to the radius of the star. Now, of course, if we combine both techniques together, so the radial velocity method that will give us the mass of that would give us the radius of the planet, we can actually do much more science with this, because we can actually calculate the mean density of the planet. So we can actually infer what the planet is roughly made of. It's a planet that is made completely out of iron, completely out of water, or if it's a gas dominated planet. We will come back later to this. Now we can take a look at the planet populations and plot it in a plot like this, where we have here the planetary mass on the y-axis against the orbital distance of the planet in astronomical units, so 1. In black, we have the planets of our own solar system, except Mercury and Mars. They are not on this plot because they are just not massive enough to be detectable with our around other stars at the moment with our current instrumentation. You see here all these colorful dots are planets that we detected around other stars, but the different colors correspond to different detection techniques. The green, so the Doppler, actually corresponds to the radial velocity. The red is the transit methods we just introduced. The orange picture of the stellar system, like the HI 8799 system I introduced you before, and we can detect planets like this. There's a few other techniques, microlensing, which is basically the gravitational lensing effect of a planet, and also transit timing variations, where we go even into more details in the transit curves. But these methods did not detect too many planets so far. Looking at this plot, you can actually identify 3 main groups of planets. One would be the cold Jupiters, that are planets similar to our own Jupiter. In this Jupiters, which are planets that are similar in mass to our own Jupiter, but they orbit the star very close orbits. That's very hot. That's why it's called hot Jupiters. And then there's another class of planets, which is the so-called superEarths or Mini-Neptunes. And these are planets of a few times the mass of the Earth that also orbit very close to their central stars. And in my talk today, I will focus on this group of planets, on these superEarth planets here. I would first like again to introduce a little bit the difference in the other stars in our own planetary system. You see here a plot of 5 planetary systems, where on the top I plot our own solar system. You see here I only plot out here Jupiter and Saturn, and I don't plot Uranus and Neptune because they're so far away we would never detect planets like this around other stars. We have here our 4 terrestrial planets, where the arrow actually marks the aphelion and perihelion of the planetary orbit. If we now compare this to the different exoplanetary systems, see already one striking difference, namely that the exoplanetary systems are actually centered in the very inner region of the system, so within 1 astronomical unit. Furthermore, we see that most of these systems actually have multiple planets, and they can also have multiple small planets and then some gas giants exterior to it. If you will, this K90 system could actually be like a down-squeezed version of our own solar system. So, and we have also a very interesting system here. For example, we find very fascinating because it's a big challenge how we can explain its the way it's formed. We have inner smaller planets or superEarths and Mini-Neptunes of a few Earth masses, gas giants, another superEarth, and then an eccentric giant planet. So it's a very challenge to explain this formation. I just want to illustrate here that the exoplanetary systems also look very different as each system compared to our own system. Then, of course, the K21 system is, in that sense, a very boring transiting in this system. But this is actually a typical example of the systems that we detect by transits, because it can actually be very likely that when we observe a planet transiting the star, we might only see 1 planet of the whole system. And we will come back to this a bit later in the talk. Now, if you take another closer look at these at the planetary systems, we can plot the period ratios of neighboring planets. So we have 2 planets that orbit the star, and we just measure basically how often does 1 planet go. And then we have here in this plot the distribution of these period ratios between the different planets. We have marked here in color different mean motion resonances. So for example, the 2-to-1 resonance implies that the inner planet goes around the star twice, while the outer planet goes around once. And this is actually very important, because if you have planets forming in the disk that interact with the disk and migrate in the disk, you would actually always catch them in a resonant configuration. But this plot clearly shows us that the majority of these planetary systems are configuration. So we have to explain the orbital elements of the different planets within a system. Furthermore, these super-Earth planetary systems, they are most often in compact multiplanetary systems. You see here in this plot several planetary systems, including also our solar system, here with the terrestrial planets. And what you can see, if you look at each system individually, you actually can see maybe some patterns within this system. Sorry? Sorry, hello?
If anyone has a doubt, please raise your hand before saying something so that I can accommodate who is there. Yes, sir, please continue.
Okay, so if you look at these systems individually, for example, for this system, you might actually see that these planets all within the same system have similar sizes, and they would also have probably similar masses. So for this system and this system, statistically, this seems very have to explain. So the point here is, how can we explain the diversity of planets and of planetary systems? And this is what I will focus on in this talk. So for the formation scenario, we work in something that is called the core accretion scenario, where the idea is we first build a planetary core, and then we could let this core grow further by gas accretion and migration in the disk. So the general picture is we have a star, and around this star we have a protoplanetary disk that consists of dust, small dust grains and gas. So in these small actually form millimeter to centimeter sized objects, so-called pebbles, by coagulation, so they just collide and stick, or by condensation, so some vapor condenses on these grains. These pebbles can then form planetesimals of like 100 kilometers in size. Now planets can actually grow by the accretion of pebbles and planetesimals and some gas from the protoplanetary disk. However, at the same time, these planets actually interact gravitationally with the gas disk. So the small planets of just a few Earth masses, they do spiral arms, exert spiral arms in the protoplanetary disk, as you see here in this simulation, which can actually allow them to migrate through the protoplanetary disk in something which is called a type 1 migration. The bigger planets, on the other hand, they actually open big gaps in the protoplanetary disk, as you can see here in the simulation. So you see a very big gap, which is then called type 2 migration. So the planets interact with the disk. At the same time, we have a disk evolution. So the disk evolves in time, which you have to take care in our simulation. To compare our planet, the planets that we simulate, the planet cross that we simulate, to the exoplanet population. You have to take care of our super-Earths, you have to take care of our Jupiters, and we also have to take care of the composition. So what are these planets made of? Of course, this is all very confusing, and there's a lot of open questions within these pictures. So a lot of research activity actually goes into the different subfields. For example, how do planetesimals form? How does gas accretion work? How do planets migrate? But nevertheless, simulations to generate planet populations that we can then compare to the exoplanet populations via the observations. Now, I would like to highlight the different concepts between the different growth processes that go in this picture, and then come to simulations of the planetary growth. So the first thing that we have to take care about is the growth of dust grains to pebbles. And the idea here is that the growth depends on how these particles, you see here, a schematic of different types of interactions of grains. So basically, when two grains collide, what is the possible outcomes of these collisions? You have two columns here that would correspond either to two equal-sized grains or to two unequal-sized grains, so a small grain and a big grain. And there can, of course, be different outcomes depending on the velocities that the grains would collide with each other. Because you can imagine, if the grains collide very slowly, they might actually hit and stick, but if you collide them very fast, they might actually just fragment. On these grain interactions, depending on the velocities of these grains. And this has to be taken into account to see how the grains can grow from micrometer sized dust to millimeter, centimeter sized particles. What is really important here is that the speed between these two particles determines the collisional outcome. So the faster the particles move, the more likely it is that you would fragment. It's the same as if you would drive in a car and you hit a wall at 5 kilometers an hour, probably not too much happen because you're in deep trouble. So really the velocities between the grains is a key. Furthermore, the particles that are larger move faster. This actually means the further you grow, the faster you go, and then this would actually lead to more fragmentation. So actually, the growth of the particles increases the velocities of the particles, which then means if the particles become too big, they would fragment again, and this actually prevents growth over centimeter decimeter. This is a big problem, because if you cannot, by this mechanism, grow above centimeter and decimeters in size, how do we actually form planets? One idea here that we can actually make use of is that the pebbles move through the disk. So they actually drift through the gas disk. And this works in the following way. In a protoplanetary disk that consists of gas and dust, the disk is hotter in the inner region compared to the outer region. And this means we actually have a radial pressure gradient in the protoplanetary disk. This radial pressure decreased gravity acting on the gas. So the gas in the protoplanetary disk does not orbit on a Keplerian speed, but on a sub-Keplerian speed. You see this here in this equation. So the velocity of the gas is the Keplerian velocity minus this quantity delta V, which is basically a small factor of the Keplerian velocity. You see this here. This eta parameter here depends on the disk aspect ratio, so on the thickness of the disk, which is basically a measurement of the temperature, and on your local pressure in the disk. The particles, on the other hand, the small dust particles, they do not feel this pressure gradient force, and they want to orbit on a Keplerian speed. And this means, as the particles that want to orbit on a Keplerian speed and the gas is on a sub-Keplerian speed, the particles feel a headwind that acts on them. And this headwind drains angular momentum from the particles, so they actually move inwards and drift inwards. And this is something that we can make bigger objects. So the way how we can make bigger objects of, for example, planetesimal size, 100 kilometers or even bigger, is that we have to concentrate the particles, and then the particles can collapse under their own gravity to form planetesimals. There's three main ways how we can make these particle concentrations illustrated here. So one is in so-called eddies. So you have turbulent eddies in the protoplanetary disk that would concentrate the particles, as you see it here. And another option would be in so-called pressure bumps. So you have a structure in the protoplanetary disk of elevated pressure where you would accumulate your particles, because the particles always want to go to the point of highest pressure. And the third option is the so-called streaming instability, which is an instability that feeds off the velocity difference between the gas and the particles in the first place. Because as the particles get drained from angular momentum, actually gets accelerated, because angular momentum always has to be conserved. So the particles lose angular momentum, but then at the same time, the gas gains angular momentum, which changes the background gas velocity. And this actually means the gas starts to orbit faster, and this can lead to an accumulation of particles. And especially when the particle cloud becomes bigger and bigger. So it's a self-feeding process. Once the particle concentration becomes actually collapse and form a planetesimal of like 100 kilometers in size. Now, once we have made objects of 100 kilometers in size, these can now further grow by the accretion of pebbles and planetesimals. You see this illustrated here in this cartoon. We have our protoplanet in the center. This radius here corresponds to the planetary Hill sphere, so where the gravity of the planet dominates over the gravity of the star. We have here two objects coming in, one pebble and one planetesimal. very well accreted onto the planet, because the pebble actually loses angular momentum due to the friction with the gas, and it can spiral in and be accreted onto the planet. The planetesimal, on the other hand, is so big that it does not feel these forces, and is actually mostly just scattered away. In this scenario, the planet grows by the accretion of millimeter-centimeter sized objects. This accretion rate is defined here in this equation, which depends on several parameters. So one is this tau f, which is the so-called Stokes number, the aerodynamic properties of a particle. So basically, it's a measurement of the size of the particles. Where larger particles have larger Stokes numbers, so we can accrete larger particles more efficient compared to smaller particles. Then the next parameter here is the Hill radius, which is basically just a measurement of the mass of the planet. Depends on the orbital timescale, and it also depends on the surface density of pebbles, so how many pebbles we actually have available. The pebble surface density is normally a how many pebbles flow through the disk as a function of time. I would like to say here that the pebble accretion mechanism becomes normally efficient once your planetary embryo is larger than around the mass of the moon. Before that, initial collisions between planetesimals might actually be needed before pebble accretion can start to take over and grow very efficiently. This is actually a very active topic of research, where we are still trying to figure out how very efficiently, especially to close masses like pebble accretion, can become very efficient. Now, as the planet grows in the protoplanetary disk, it starts to interact with the protoplanetary disk gravitationally. And what happens is that the planet starts to open a partial gap in the protoplanetary disk. You see this illustrated here in this plot, where we show the perturbed density around the planet. You see here the planet. You see here we have an underdensity. We have here overdensities exterior from a simulation. Why does this happen? And this happens because the planet exchanges angular momentum with the protoplanetary disk. The planet wants to give angular momentum to the gas exterior to the orbit. But if the gas exterior to the orbit gains angular momentum, it becomes accelerated and moves away from the planet, which means that the planet slowly starts to open a gap around its orbit. You see this illustrated here in this plot, where we plot the orbital distance from the planet. So the planet is at 1 against by the Keplerian velocity. So as I said before, there's a radial pressure gradient in the protoplanetary disk. So you see far away from the planet, the gas orbits on the sub-Keplerian speed, so your pebbles would all drift inwards. However, close to the planet has accelerated the gas, and this can actually lead to super Keplerian velocities exterior to the planet. So as the pebble comes in here, as it loses angular momentum, it suddenly here would gain angular momentum by the interactions with the gas phase, which means drift inwards. Instead, it will be stuck here exterior to the planetary orbit. But if the pebble is stuck exterior to the planet, it can of course not be accreted onto the planet anymore. So pebble accretion would actually stop at the so-called pebble isolation mass. So pebble accretion basically self-terminates once the planet becomes big enough. This pebble isolation mass depends very strongly on the disk properties. So, for example, on the disk viscosity, because the viscosity always works against opening the gap and tries to close the gap. And it, of course, also depends on the particle sizes drift at different speeds. Now, we just need one more ingredient for our model, and that is planetary migration. So the idea here is that we have here a simulation. Again, the color bar gives you the density perturbation. We have here our planet, and you see that the planet exerts spiral arms in this protoplanetary disk. Through these spiral arms, the planet exchanges angular momentum with the protoplanetary disk. And this means the planet has to migrate. You can actually calculate these torques that arise from the spiral arms. You can actually do this analytically, as it was done already 40, 50 years ago. And we would come to the conclusion that the torque coming from the outer spiral arms wins against the torque from the inner spiral arms. But this means the planet has to move in, because the contribution from the outer part is negative, and you would be pushed inward. So the planet actually moves through the disk. And this migration can actually be very fast. The lifetime of the protoplanetary disk. So it was a very big problem in the past, because the migration timescales that we get for the planets are on the order of like 10 to 100,000 years, but the disk lives millions of years. So basically, you would expect all planets to migrate into the inner disk, which of course is not the case. However, there's additional contributions to planetary migration. One is the so-called co-rotation clock. You see the illustration here in this cartoon. You can also take a look at the review from Klein-Nelson 2012. So you have here our planet, and you see here by the arrows indicated the velocities of the gas in the frame of the planet. So the gas, sitting here at the position of the planet, the gas interior to you is orbiting faster, so it gains on you, while you move slower, so you gain onto the gas. So what happens here is that the disk has a gradient of temperature and surface density in the disk. So your material reflected by the planet to an outer orbit, it goes from a hot, dense region into a cooler, less dense region. What then happens is that your material would adiabatically expand. So you would generate an under-density exterior to the planet. Furthermore, if the material comes from the outer disk and is deflected to the inner disk, you have basically the same effect in the opposite direction. So cold material from a less dense environment gets transported into a denser, hotter region. So the material, so you would generate an over-density interior to the planet. And this over-density interior to the planet and the under-density exterior to the planet also generate a torque acting on the planet. And this can actually lead even to outward migration of the planet, because if you have, because the torque here would basically just pull on the planet and try to push it outwards. This, of course, depends very, very strongly on the initial protoplanetary disk structure, so on its temperature and its surface density and its viscosity. We can make use of this and actually now look at the formation of these super-Earths. So we can look here at the formation for rocky super-Earths. You see here a plot where you have planetary mass against a semi-major axis. We look here at two different sets of simulations, where the difference is just the pebble flux. So how many pebbles do we have available? As I said before, if you have a low amount of pebbles, you will maybe not grow too much, but if you have a large amount of pebbles, you can grow faster. You see here the difference in these systems. For just make like mouse-sized embryos, while with a larger pebble flux, we can actually make super-Earth systems of a few Earth masses. To illustrate how this actually works, you can look at these plots here, where we show the planetary mass, the semi-major axis, eccentricity and inclination of the planets as a function of time. Initially, the planets start to grow very smoothly, and this is due to the pebble accretion mechanism. So the planets accrete pebbles and they smoothly start to grow. At the same time, these planets actually start to migrate inwards due to the inward migration. However, then you see here, the planets become actually close to each other and gravitationally interact. You see a few of those lines that actually stop, which actually indicates a collision. You also see this here in the mass jumps. So the system actually also evolves gravitationally. Now, if you compare the different simulations with different amount of pebbles, we can already see a difference in the system. So we show here on the left the planetary systems after 3 million years, so after the end of the gas disk phase, and here after another 100 million years of integration, where we just have the gravitational forces between the bodies. During the disk phase, we have pebble accretion, we have planet migration, but then the disk gas dissipates and the gas is gone, and then we only have the gravitational interaction between the bodies. If you look at the different systems, you see here that our planetary systems that had a low pebble flux would actually grow to super-Earth-sized planets after the gas phase. And this indicates that these planets could not accrete any gas from the protoplanetary disk. These systems would then also, not with scattering events, try to always remove a resonance. On the other hand, If we have a higher pebble flux, we can make our super-Earths directly already during the gas phase. And these systems can then be in resonance, and they could have hydrogen and helium envelopes, which they can hold onto even after another phase of scattering events. But we will, I will illustrate this so in a few slides in more detail. So now we also have to take into account the evolution of the planetary disk itself evolves in time. What it mainly does, it loses mass and becomes colder. You see here a plot of the disk temperature as a function of orbital distance, where the different lines correspond to different times of the simulation. So we see here a temporal evolution from the light blue line towards the black line in 3 million years. This blue line here, this horizontal blue line, corresponds to the water ice line. So in the protoplanetary disk, in the inner regions, it is very, and in the colder region, you can actually have water ice particles. And this actually changes our perception of how particles can grow, because the idea here is that water ice sticks actually a bit better compared to silicate particles, so we can have a larger particles compared to the inner disk where we do not have a water ice available. So the growth might actually be different interior and exterior to the water ice line. Now, if we take this, if we can redo the same simulations and see what we can get. So I will show you now a movie where we have the planetary mass against the semi-major axis. And you see here the initial setup of our movie. So you have here in blue our water ice line. So interior to it is hot. We only have rocky particles, and exterior to it we have icy particles. Then this black line corresponds to the pebble isolation mass. So how large a planet can grow just by the accretion of pebbles bond to zones of outward migration. So if a planet is interior to one of these zones, it would actually migrate outwards. And if a planet is exterior, it would migrate inwards. So we can look at the movie here. So you see here our planets initially growing by the accretion of pebbles. As the disk evolves, you see we form a system of several planets that is stuck now at the moment in this region of outward migration. But then as the disk evolves, moves towards the inner edge of the protoplanetary disk, that forms a system also collides. I will play the movie again because it goes very fast. So first, please focus here on these planets on the color bar, which actually indicates the water ice fraction. So blue means a large water ice content, and red a low water ice content. You see the planets in the outer disk, they start to grow more efficiently because the water ice pebbles are slightly bigger than the silicate pebbles. So they grow and then they start to migrate inwards. You see that the growth of the planets depends also on the away you are, the longer it takes for you to grow. So you have some planets that just come towards the end of the disk lifetime into the inner region. In the end, what we are left with, if I can go to the end of the movie, is a system of inner super-Earth planets that are in a resonant configuration, because migration always tries to push you into a resonant configuration. Now, let me go into this a little bit more in the detail. So here the result of one simulation where you plot the semi-major axis, the planetary mass, the eccentricity time. This gray band here, this gray horizontal band here, corresponds to the dissipation of the gas disk. So in the first few million years, we have pebble accretion, we have our migration, and the disk additionally damps eccentricity and inclination. Once the gas disk dissipates, we only have the gravitational interactions between the bodies. So what we see happening here is, again, the mass just increases very smoothly due to the accretion of pebbles, but then the planet stops growing. This is when the planet reaches the pebble isolation mass. At the same time, these planets start to migrate into the inner disk, and they form a system of resonant planets in the inner disk. Dissipates, we can have a dynamical instability, so gravitational interactions between the planets that would actually throw some of the planets out of the systems, or you can have collisions, as you see here. So the mass grows here. For this planet is, of course, true to a collision. So two bodies collide and make a bigger body. And this happens after the end of the gas disk phase because we lose the damping of the eccentricity and inclination of the gas disk. So you see this here actually, if you look at the eccentricities, you see the eccentricities are the gas disk dissipates, you see that the eccentricities actually increase, and also the inclinations in the gives rise to overlapping orbits and then collisions. We can now take a look what it actually means for the observation of planetary systems. So if you have multiple planets that are in a very flat configuration, and we look at these systems, maybe we can observe nearly like all five planets by this transits. However, if these planets underwent mutual collisions and have mutual inclination, though there are more planets hidden in the system. And this is actually true also for the solar system, because all the planets in the solar system also have small mutual inclinations. So if you were outside of the solar system and want to observe the solar system with transiting, you would see a maximum of only 3 planets transiting. I mean, of course, given so that you could really observe transiting planets of a few hundred years orbit. So the point here is small mutual inclinations can actually change our perspective of how many planets we find with the transit on one planet. We illustrate this here also from our simulation, where we show here the cumulative distribution of the planets for the number of planets detected by transits in the inner system. The gray line that you see here corresponds to the observations with the Kepler Space Telescope. We see that we have a huge amount of planets where we only detect one transiting planets. We now have, for our simulations, we have 2 sets of the red solid lines, which mark the systems that remain stable. So we migrate them in, they stay in a resonant configuration, and then they never undergo an instability. The red dashed line, on the other hand, marks the system that actually underwent instabilities. So where we had scattering events, planetary mergers, and so on. The corresponding black lines show actually the synthetic detections of these planets. So if our planetary systems that we make in our computer simulations were the real planetary systems, how would we observe them? And to the stable system, so we have many planets in the system, and the black dashed line corresponds to the systems that underwent instabilities. Now, the green line corresponds to a mixture between stable and unstable systems, because we know that even though the number of planetary systems that are in a resonant configuration is very low, they still exist. So there must be some systems that are stable. And with a mixture of like 95 unstable and 5% stable systems, you can actually explain the Kepler observations very well. Additionally, I would really 5% unstable and 5% stable system is actually a natural outcome of these simulations. So it's not that we had to mix and match, so to say. To illustrate this point a little bit more, we show here again the same distribution of the detected planets. In gray again, the Kepler planets, and the color coding actually corresponds to the number of planets in our simulation. So if in our synthetic observations, if we would detect one transiting planet, the color planets within our simulation. So you see that mostly, if we detect one transiting planet, most of the time, the real planetary systems actually have 2 or even 3 planets. So basically, there would be hidden planets that we do not see by the transit observation. And this trend basically holds for all the different number of detected planets. We can go a little bit more into the statistics. So first, I would like you to focus here on this plot on the top left, where we plot the cumulative distribution pair. So you have 2 planets, and we check the period ratio between them. The solid lines in this plot correspond to the stable systems. So the systems where the planets just migrate in and are stuck in a resonant configuration. You can see this really illustrated here. So in this cumulative distribution, if you have these big jumps, it actually means there's a lot of planets with this configuration. In this case, you see here, the purple line increases quite a lot at the 4:3 mean or motion period ratio. So this means for this blue set of simulations, a lot of planets are not. In contrast, the dashed lines, they correspond to the unstable systems. So the systems that underwent an instability after the gas phase. And we see that this distribution actually matches the observations from Kepler. So in this gray band, actually very well. This again also points to what I was saying before. If we now look at the inclination between the planets, so you see the systems that are unstable, they actually have very low mutual inclination. So we probably the simulations that show unstable systems have much larger inclinations, which basically explains the effect I was talking about here. Now, I would like to focus on the composition of super-Earths. So what are super-Earths made of, and to what fraction do they consist of different materials? So for this, I would first like to introduce this very complicated plot from Zheng et al. 2016, where we show the planetary mass against the of the planet. In this plot, there are several lines. So for example, the red line here would correspond to a body that is to 100% made out of iron. Of course, a body like this does not exist, but it already gives you a very good illustration of what happens. So what this curve basically tells you, if you have a planet that is 10 Earth masses, what would be the radius of this planet if the planet would be made 100% out of iron? So you would see that would be around 1.5 Earth radius. This would be a planet that is made to 100% out of water. And you see, if you go for the same planetary mass, we actually have a much larger planet of like 2.6, 2.7 Earth radii. And this diagram can now give you the first information of what a planet would actually be, could actually be made of. So these planets down here in this part of the diagram most likely do not have a large water content compared to the planets that are further up in this planet. Then you see a lot of these planets here around 3 to 4 Earth radii, hydrogen helium envelope, which boosts up their planetary radius, also given their planetary mass. You also see in this plot the error bars of the observations. So you see there's still a lot that we have to improve in our statistic to really understand a planet formation, to really constrain this from the internal composition. So instead of like going into the details of all the different compositions, I would rather focus on two extremes, rocky and water world, because we have to because this is something sense. So where does this come from? So we can take a look at the planets that we observe. We plot here the planetary size against the stellar light intensity relative to the Earth. So the larger this number is, this means the closer the planet is to the host star. The black dots correspond to the detected planets, and the color bar in the back gives you the relative occurrence of these different types of planets. And what you see here is actually, you see a distribution where it seems that we have a lot of planets below like 1.5-ish Earth radii, and a lot of planets around like 2.5 Earth radii, and not too much planets in between. And the question is, how could this actually arise? And one idea here is that this is actually related to the loss of the atmosphere of these planets. So you have a planet that forms, and it actually has a surrounding atmosphere, and then the planet could lose this atmosphere due to the gravitational, to the evaporation. So basically the intensity from the star heats up the atmosphere and basically blows it away. We can now take a look into this in a statistical sense. So we show here the normalized fraction of the planets as function of their radius. The green curve corresponds to the Kepler observation. So you clearly see these two peaks in the distribution. Now we can do simulations where we actually can how they would evolve in time under the assumption that, for example, external photoevaporation would blow away their atmospheres. And if we now take a look at these two different set of simulations, we actually see that, for example, if we follow the blue line, that would correspond to the idea that we have an icy core that is made predominantly of water ice in an atmosphere, and you would blow the atmosphere of the smaller guys away. You arrive at the blue curve, so you would have a valley in the distribution compared to the observation. So it's clear that the water ice. On the other hand, the or simulations where the inner planet is on a rocky distribution actually matches the Kepler observations very well. So we have the peak here at the same set of simulations. So this, of course, now corresponds to the idea that most of these small planets are actually rocky in nature. Of course, there's a lot of debate in the literature about the position of the valley and how deep this valley actually is. The valley in itself is not caused by the evaporation of the atmosphere from the star, but actually by something which is called the core-powered mass loss, where the planet is initially so very hot that it just blows away its own atmosphere. So it's a very big debate ongoing now in the exoplanet community. How can we explain the composition of these planets and what they are really made of? So I think the bottom line here is that it is very clear that we cannot assume that all super-Earths are rocky and that all super-Earths are icy. So this would just be naive. If we compare this now to remember the color bar, and you saw that basically all of our planets were blue, which basically means they had a large water ice fraction. This, of course, is inconsistent with the observation. So the question is, how can we actually make these planets with a rocky composition? The idea here, of course, is that these red planets here could actually correspond to the second peak of the planetary systems. 1 second. Sorry, there's a storm coming. Okay. How in our simulations could we actually make these planets rocky? So the idea here is that we can that the planets interior to the water ice line have to grow fast. And we can actually achieve this through one simple idea. The first one would be that we actually have larger pebbles in the interior region compared to what we assumed initially. Initially, we assumed that we had millimeter-sized pebbles in the inner regions of the protoplanetary disk, because that corresponds to the sizes of chondrules that we see in our own solar system. Larger pebbles in the inner region, the planets can grow faster, and we can actually make rocky planets, as you see here in this set of simulations, where each line corresponds to a planetary system and the different color to a different composition. So the centimeter-sized pebbles, as I said, seems to be okay with the growth models for pebbles, but it might be in conflict with the control sizes in our own solar system. Another option is the heating by aluminium-26. So aluminium-26, a metal that decays on is a half-life time of a few 100,000 years, and to the radioactive decay, you actually generate heat that could evaporate the water away from your planetesimals and from your planets also, which then would basically mean that you would accrete mostly rocky particles. Another open question is actually the ablation of volatiles during planet formation. So when your icy pebble comes in, your planet is actually hot, and your pebble could actually evaporate in the planetary atmosphere. And the question is the planet. So there's still a large discussion going on how we can explain this. One other option that we can take a look at is actually the planet migration, because in the simulations that I've showed you before, the planets actually finished their formation exterior to the water ice line where it is wet. So they would always accrete the water-rich pebbles, and then they would migrate inwards. So the idea here is that the planets would migrate outwards close to the water ice line. So you see here a so-called migration map, where the color coding gives you the torque acting on the planet. So if you have a positive torque, you migrate outwards, also indicated by the arrows, and this red line corresponds to the water ice. So in the simulations that I've shown you in the past, the planets would actually grow in the outer regions of the disk, would then be stuck in this region of outward migration, finish their growth there, and would become water-rich planets. If the planets, on the other hand, would actually always migrate inwards, then they would actually change their composition. You see this illustrated here, where we show the planetary mass as function of orbital distance. So the planet starts to grow, it accretes a lot of, but then it crosses the water ice line, and then accretes mostly rocky materials. And in the end, we have a body that has a lower water fraction compared to a body that stayed always in the outer regions of the disk. So the migration direction close to the water ice line is very important for all these planets that we observe. So the as I said, the migration direction plays a role in this. That actually, as I mentioned before, the migration direction depends crucially on the disk properties in the disk. So knowing the disk would actually help us to understand planet formation. So this actually brings me to the summary of my talk. So the formation of these planets is a constant interplay between accretion, migration, disk evolution, and planetary instabilities. We can actually distinguish two different types of planetary systems within this framework, depending on the amount of local of pebbles that are available. So for a low pebble flux, so for a slow growth, we have a terrestrial planet growth mode. So basically this means the planets grow mainly by collision, and we would then have no resonant planetary systems left. While in a high pebble flux scenario, the planets can grow fast during the gas disk phase of the disk, which would then result in resonant systems, also with potentially hydrogen helium atmospheres. So we could maybe distinguish between these two different systems. Additionally, our simulations indicate that these instabilities after the gas disk phase are really needed, and we can actually match with this the period ratios of the observed exoplanets. Our simulations indicate that there's still a lack of understanding between what are rocky and what are water super-Earths and how they are made and how do they fit in with the simulations. We know that the evolution of the ice line makes the systems mostly wet, because as the ice line moves inwards, inner planets can accrete water ice. There's of course a lot of open questions within this talk regarding these sets of simulations. For example, what are the pebble sizes within these systems? How do the planets migrate close to the ice line? How does the disk exactly evolve? Or what is the embryos? For example, if the planetary embryos would only exist in the inner regions of the disk, and there would be no planetary embryos in the outer regions of the disk, we would probably automatically make only rocky super-Earths. So there's still a lot of open questions in this active field of research, and I hope I could give you a little glimpse of what kind of simulations we do and how we compare this to observations. And thank you for your attention, and I'm happy to take any questions.
Thank you, sir, for the talk. It was very informative and engaging. So there are a few questions in the chat. I will read them out. There's a question from Aritra Roy. She's asking, what is the criteria by which we demarcate between hot and cold Jupiter and super-Earths?
Yes. So for the hot and cold Jupiters, it's mostly determined basically by the distance of the planet. So normally we define a hot Jupiter by a planet that is within 0.1 astronomical units, so that's very hot to the star. Cold Jupiters are normally the planets that are exterior to 1 astronomical units. In between here, there would be the warm Jupiters. They are extreme. They are not that common. So it's still like an active field of research to understand the origin of these warm Jupiters that are based in hot and cold Jupiters. Super-Earths are planets. The definition is a bit more loose, let's say. So it's basically mainly planets of a few times the mass of our own Earth. If you want to go more, let's say, within the radius definition, so these would correspond to planets that would be below 4 Earth radii, so they would be smaller than Neptune. So they're also called sub-Neptunes because they're smaller than Neptune.
Thank you, sir. Next, we have a question from Suhas. He's asking, what radiation results from the pebble acceleration?
Sorry, could you repeat?
What radiation results from the pebble acceleration?
Radiation?
Yeah, the question says.
No, the radiation has nothing to do with pebble accretion. So the idea here is basically that as you grow your planet, the decay from aluminium-26 would generate heat, and that heat would heat up the planet, which could give temperature to could rise temperatures to such large values that the atmosphere might be actually be blown off and the water might be lost. But pebble accretion in itself has nothing to do with radiation.
Okay, sir. Thank you. Next, we have a question from Deepan. He's asking, is there any effect of the planet's spin axis inclination on the pebble acceleration rate?
And a question. I think this has not been studied in detail yet. No, it's a very interesting question. We know, for example, that when you have, for example, the collapse of a pebble cloud to make planetesimals, that then the spin alignment is actually crucial to explain certain features of the objects of the rotations in the Kuiper belt. There's a very nice paper from David Neswani from 2019 about this, but this is really more in itself. It has not been studied yet, so it's a very good question.
Thank you. Next, we have a question from Drishika Nadella. Does the star's magnetic field play any role in this?
Excellent question. In our simulations, we do not take the magnetic field of the star into account. So for the formation processes that happen far away from the star, it would not. However, of course, if the planet is very close to the star, it will actually change the shape of the planet and so on, which might actually be observable. Furthermore, during the protoplanetary disk stage, the magnetic field is very important because the magnetic field sets actually the level of turbulence in the protoplanetary disk. So something which is called the magnetorotational instability, and that scales with the magnetic field, and that then drives the level of turbulence. So the viscosity in the disk. So how fast does the disk evolve in time? Actually be. So the magnetic field plays a role in that sense, but for the planet formation process, for example, like pebble accretion or planetesimal accretion, it does not play a role.
Okay, so thank you. Next, we have a hand raised from Advait. Please unmute yourself and ask a question.
Yeah, am I audible?
Yeah, I hear you.
Yes, you are audible.
Yeah. So my question was, can you go to that? You had talked about the Stokes parameter and everything.
Wait, which slide? This one?
Yeah, this one only. Yeah. So I didn't really understand this MC dot this relation. So what is it exactly like talking about the relation?
Sorry. So this m.c is the accretion rate onto the planet as a function of time. So basically, how fast does your planet grow? And the growth of the planet depends on the Stokes number, which is basically a measurement of the size of the pebbles. So basically, bigger pebbles are accreted more efficiently.
So here we are seeing a planetesimal is like it just gets deflected and your smaller pebbles get accreted. So the Stokes number, it says if it's a larger thing, so the Stokes number will be greater, so the accretion should be higher, right?
Yes. However, there's a excellent question. No, you're absolutely correct. However, there's a drop in the basically how the particles couple to the gas, which I did not mention. Here, larger and larger. So if the Stokes number increases way above 1, then they do not interact with the gas anymore. So they don't feel the gas track. So you would only feel the gravitational interaction. So the idea here is really that the small pebbles, they would accrete faster if the Stokes number increases up until 1, but then they would basically the efficiency goes down again. So basically, if you would make a plot where you plot here the accretion efficiency as a function of particle size, you would have basically around 1. So if you become planetesimal sizes, this effect does not play any role. So the idea here really is that you can accrete the pebbles efficiently due to the interactions with the gas that robs them of angular momentum. But the planetesimal does not care about this.
Okay. And
you can also take a look here. in this paper from Johansen Lamprecht 2017. It's a review on this process. They also explain it in more detail.
I had another.
Please refrain to one question per person because we have more people. You can follow. Next we have Aditya Roy. Please unmute yourself and ask your question.
Hello, sir.
Yeah, hello.
Yes, sir. Am I audible?
Yes, yes, I hear you.
Yes, sir. First of all, thank you, sir. It was a very interesting session. And sir, my question to you is that collision process of the dust particles. Sir, was that an inelastic collision or an elastic collision? And if it is an means this process, is it relevant to the protoplanetary dust accretion?
Yes, excellent question. So in our simulations, we have perfect mergers. So if two planetary embryos collide, they basically make one object that is equal to the mass of the two previous objects. There are simulations that take into account the some mass. They do not change the general outcome of the simulations in the sense that still these collisions are very important. 1 second. Okay, but it does not change the general outcome of the simulations.
Thank you, sir.
Okay, so I was informed that you have to leave at 7. So do you mind taking more questions? Or
I have questions, but then I have to run and pick up my kid from daycare.
okay, sir. We have Drishika, I guess. Yeah. Drishika, please unmute yourself. Okay, so there is some technical difficulty, I guess.
Yeah, I have one question. I think I was disconnected.
Yeah, go on.
Which type of radiation is dominated in the pebble accretion disk?
Sorry, I didn't understand that.
Actually, this question has been answered already.
Oh, okay. Oh, sorry. Actually, I was disconnected that time. Okay.
We have a question from the chats. How these pebbles acceleration results explain the formation of planetary satellites? Does it happen at later stages of evolution?
Oh. Yes. So for satellites, it's a more complicated issue. So the idea here is that basically the same process that happens in the protoplanetary disk could also happen in a circumplanetary disk, so the disk that would form around the planet in itself. So there's actually some work from the group of Anders Johansen about how pebble accretion could explain the moons of Jupiter. The still a bit unanswered question is, of course, how does the solid material enter the circumplanetary disk? Because as you see here, the planet actually opens the gap in the protoplanetary disk, and the pebbles would accumulate exterior to the planet. So how do the pebbles actually reach the circumplanetary disk in order to make the moons? This is still a question that we're trying to answer and to understand. But if enough pebbles can actually make it to the disk, then pebble accretion can also explain the formation of the moons around giant planets.
Okay, sir. Thank you. We will take one more question, last from Anna Kavin Kumar.
Hello, sir. It was a lovely talk. So I had a doubt regarding our own solar system, where we couldn't form such a similar system, such as a super-Earth or a mini-Neptune. Why is that? Is it due to the fact that Jupiter and Saturn moved during the migration, or is there any other?
Yes, that's an excellent question. Of course, the solar system is in a way a bit more of a mystery than exoplanet systems, because you have many more constraints that we have to take into account, because for exoplanets it's mostly just mass and radius. So within the pebble accretion scenario, the idea is that Jupiter's core formed very quickly and reached pebble isolation mass. And then the moment the core reaches pebble isolation mass, basically the inner planetary system is starved exterior to the giant planet's core, in this case Jupiter, and the inner system would then not have pebbles anymore. So basically the growth would start. So basically you would arrive at a scenario as is illustrated here. So basically you cut the flux of pebbles to the inner system, and then basically you stop your growth. You might arrive at like Mars-sized embryos that then can collide and form the terrestrial planets in our own solar system. There's a large body of work going into this. A very nice paper from Cryer et al. 2017 that uses the same mechanism to explain some cosmochemical differences between carbonaceous and non-carbonaceous chondrites within the solar system, just exactly by this mechanism. So the idea here really is that you have to cut the pebble flux into the inner disk of the solar system in order to just make the terrestrial planets instead of the super-Earth planets. This, of course, at the same time implies actually a correlation between giant planets and inner terrestrial planets. And we cannot yet fully observe terrestrial planets in exoplanetary systems, but I think this is something we can nail down in the coming years. So this will actually be a very, very interesting test of this theory.
Okay, sir. Thank you.
You're welcome.
Okay, sir. Thank you. So there are a lot of questions, I guess, but since unfortunately you have a time constraint, I would like to end the talk here. Thank you, sir, very much for joining us and for this beautiful and informative lecture.
Yeah, thank you very much.
And thank you everyone for joining us.
Thank you very much. Thank you. So, I mean, if you, so I can recommend some review papers for pebble accretion. There's the paper from Johansen and Lambrecht 2017 that deals with a lot of the processes of pebble accretion, if you want to take a closer look into that mechanism. So thank you very much for the attention.
Yes, sir. Thank you. So we'll approach you and you can recommend us the paper so that we can share it with our public.
Yeah, absolutely.
Okay, sir. Thank you very much.
Yeah, thank you very much. Bye.
So thank you everyone for joining us. I hope it was an informative talk and everyone enjoyed it. I understand there were a lot of questions. We couldn't accommodate all of them, but we'll try to have more such lectures next time and keep in touch with us. Thank you very much.